So I'm here with Rodrigo, Ericsson Antenna System. Great to see you, Rodrigo.
Likewise.
Tell us a bit how we can make the antenna part of the AI-driven network.
Well, AI networks or programmable networks require a lot of data, accurate, with high integrity, in a secure way to feed algorithms that can take decisions in an accurate manner. The positioning of the antenna, even the location of the antenna, is not necessarily super accurate in the inventory systems of the network, of the operators. And why that's a problem? Because if you have some sort of RF or some sort of tool associated to design or optimization, it's super important that you understand the exactly precise location of whatever object that you have in the network, so you can understand how the RF propagation is going to shape, right? Mm-hmm. Not only that, if there are physical alterations, as an example on the antenna tilt, that has a huge impact on network performance. As an example, 1% tilt deviation on the antenna implicates into 25% less throughput on the cell edge for the subscriber.
Wow.
And the problem is that without those sensors, without that information, you really don't know what's going on other than there is some degradation on performance. So the way the antennas are helping the AI-driven networks is by providing accurate, trustworthy information. So those antennas are becoming some sort of, they have sensors. That particular one has 2 GPS, is a gyroscope, so which allows to understand not only the precise location, but also all the inclinations, azimuth, and roll as well of the antenna, which feeds those AI systems with accurate data to take proper decisions.
Okay, so give us an example of how, with these sensors, you're generating data from the antenna, previously a passive device, how that feeds through and actually delivers benefit into the network.
So let's take a look at a real case. So the device that we have built in those antennas are called AMU, Antenna Mounting Unit. Mm-hmm. And like I said, they have sensors, GPS, gyroscopes, etc. So with AMU, you start to have visibility that in data that you didn't have before. As an example, over time, you do have thermal expansion, you have wind loads that might change the tilt. Again, without the AMU, you're blind. You don't know that the tilt has changed. It requires you to go to the site to do a manual audit, which is quite expensive, time-consuming, right? So here's an example where the tilt has been changed by 1 degree. And you can see here the capacity, the coverage, and SINAR as it is. Based on that sensor, there is the ability to trigger an alarm to DNM, and that can be ingested by an RF that can send a command to the remote electrical tilt of the antenna and adjust. So basically, you can define a closed loop for the network self-heal, so to speak, right, without human intervention. So that's one example. And as you can see here, huge significant impact on capacity, coverage, and SINAR. Okay? Another example here, it is location. So as I said before, we have done some studies, and typically speaking, only 40% of the location of the sites in the inventory systems are really precise. The remaining 60%, well, it's not a big deviation, but it is a deviation from where they really are. Mm-hmm. And why that's a problem? Again, if you're feeding algorithms that rely on accurate data to understand RF propagation, to do a design optimization, accurate data is the most fundamental layer of information, right? So with AMU, due to the GPS, therefore, you do have the ability to fully comprehend where the site's located. So there is a discrepancy here, right? That's the real location, but the antenna on the digital twin was here. So then you make sure that your digital twin, your data is fully aligned to what is in reality on the field.
So it's a big deal to bring, I guess, passive equipment into the active network managed domain, really.
Yes, I mean, those antennas are becoming smarter. They're not so much more passive. There are sensors, there's the ability to do certain functions remotely. not to mention that they have significant impact on the performance of the network as well.
Yeah, those stats you showed about a 1 degree off of tilt,
yeah.
That's such a big impact.
It is.
I was very surprised when I first heard
yes.
that.
Yeah.
Rodrigo, to close us out, what are some of the next steps for operators that you would say?
So I think one key takeaway is that typically speaking, operators look at data sheets to make the determination on which antenna is the best for their network. The problem with data sheets is that they don't tell the whole story. They are not going to tell you all the capabilities that I described, right? How they can become engine for AI-driven networks. They don't provide information associated to other parameters like antenna efficiency, beam efficiency that are super relevant for the performance of the network. Mm-hmm. So you need to really look at evaluating the antennas as in a holistic manner, looking at the 3D pattern and fully understand what is the impact to your network. I mean, we have seen significant improvement by only replacing antennas. We see up to 30% downlink and uplink throughput improvements. If you think about it, is the cost of modernizing an antenna is nominal to the alternative, which would be adding new sites, or even a spectrum to be able to cover those gaps or achieve the performance that you're looking for. So antennas are the unsung hero. People take for granted, but I mean, they are super important, as we have proved here, not only for the performance, but to feed the AI programmable networks of the near future.
Rodrigo, sounds like a ton of innovation. Thank you very much.
Thank you so much. Good to see you, Gabriel. Thanks for the opportunity.